So today we're going to talk about backends for frontends with GraphQL. So maybe a couple of words about me. So as Oscar mentioned, I was heavily involved in work related to UI development. There was a lot of interesting stuff going on there. But now I'm kind of more into full stack development, architecture, cloud stuff, DevOps, and everything related to that stuff. So, and today we are going to speak about, the problems of maintaining an API which kind of tries to serve the need of different clients. So it's quite popular now that you have a single API for a mobile app, for a web app, for a watch app, for whatever app. And that raises some technical and organizational questions. So, and till recently, we personally as a company, we didn't really consider them properly. So, and when doing that, we kind of stumble upon the backend for frontend pattern, which kind of really changed our mind, how we think about it, and solved a lot of problems for us. I would like to share that experience. We will also be talking about GraphQL as a communications protocol for implementing this pattern. Unfortunately, due to time constraints, we won't be getting into a lot of details. We won't be able to cover all of the GraphQL stuff, but my colleague Oleg will give you a talk about this tomorrow, and he will kind of give you a more technical walkthrough through all of the stuff and all of the tools and libraries which are available in this ecosystem. So maybe a question you are asking yourself now is, why am I talking about API design on a front-end conference? Because I think that for a long time we thought about API design a bit wrong. So API design came from domain-driven design, came from the concept of bounded context, stuff like that. It was never really driven by the client, by the end users, who are, if we're talking about public APIs, are the front-end developers. And when it comes to creating front-end facing APIs, apart from server-to-server APIs, there are a lot of things we need to consider. And the initiative, kind of for pushing the priorities, that lies on the front-end team. So this is why I would like to share this talk with you, so to make sure that everybody understands that this is not the concern of the backend team. It's a cross-cutting concern, and everybody should play their role. So maybe to give a clear idea of what problems we're trying to solve here, let's consider a simple picture. Like this could be your typical architecture if you're working in a company, let's say doing a internet store of a website which sells vintage cars. And here's what you have. So you have a web-based client, which is mostly desktop-oriented because, well, no, the expectation was that most of the users would be sitting behind their laptops or a desktop. So the user opens the browsers, he enters your app. You have a bunch of downstream microservices, each playing their own role. You have a microservice for serving product information. There's an order service, a payment service, so whatever you need. And you kind of have a facade between the two, abstract the way all of the downstream services. Yeah, the facade could be RESTful, it could be RPC-like, doesn't really matter. It might be tailored a bit for the needs of the web UI, so it's probably not a pure REST API, so you might combine some resources to save some traffic, and all in all, but it's like a general API. And so far, so good. Yeah, that works. At some point, you and your boss, you can decide that, okay, your business is booming, we now need to support mobile. What do we do? How does that impact your API? Well, the first thing that comes in mind is the purely technical problems. So mobile networks are slower, they're more expensive. This means we need to make sure that we don't load any unnecessary information, and we are conservative in the amount of actual calls that we need to make to our API. The deeper problem is that the flow of how the user interacts with a mobile app might be completely different from a web app. For instance, on a web app, to buy a car, you might make the user to fill a gigantic form. Yeah, on a phone, you might place emphasis on an express checkout feature, which would just allow you to buy a car with the press of a button. It kind of does the same thing under the hood. It places an order, but the amount of but the type of calls which are made, the type of data which is sent around may be completely different. Thus, the APIs will be different. It is manageable if you kind of have two clients. What you can do, you can, for instance, do different endpoints or different methods for different clients. So you can have a product list method for a desktop, which will kind of return the expand fully fledged content for the product list. And you can have one for mobile, which will, I don't know, return the shorter version, just the titles and the price. Could be, but it kind of forces you to predefine your clients on the backend side, and your kind of design becomes blurry. Yeah, so we are moving away from the domain-driven design to a domain plus consumer context-driven design, whatever that works. There are some protocols which try to address this problem, like OData, which kind of allows you to use an SQL-like syntax on top of a REST API, which will allow you to do filtering, picking out particular columns. But it's quite complex, and it also has limited tooling support. And, well, the last and probably the worst idea you can pick off, because you can try to invent your own protocol to do that, which is usually a bad idea because you need to maintain that. So, but you can manage to client. But after that, your boss comes and says, okay, now we want to also accept orders by phone, which means that you need a human operator and some kind of admin interface to place an order. And we also want to support smartwatches, because apparently buying vintage cars over smartwatches is a thing. So now you're screwed, because now you have 4 different types of clients, each with their own technical needs and each with their own kind of workflow and interaction flow. And on the API side of you, that means that you need to support all of this mess. Your performance suffers for everybody because, I mean, realistically, there's no way you can address all of the performance problems that we have. And eventually, your backend team becomes really stressed because they need to manage both 4 clients on top and also keep the integration sync. So it causes pain for them. So how do you address that? That's where backend for frontends come in. So what is a backend for frontend? In short, BFF. BFF is essentially a data transformation layer on top of your existing API. So what it does, it receives the calls from the frontend, does all of the downstream calls, aggregates the information, and returns it in a way which is particularly tailored for the experience of the client. It doesn't have any backend logic in itself per se, so all of the backend logic is still done in your downstream microservices, but it kind of only handles data transformation and data aggregation. And how would that look like in our case? In our case, when we come back to the 2-client problem, each of the client would have their own BFF. So essentially another backend, which is written in whatever, whose job is to kind of expose a particular API for a particular client. So for instance, the work of the desktop BFF would be to fetch all of this rich data information and present it to the web UI, while for the mobile BFF would be implemented in a way to return leaner product information. For instance, emitting images, text which you might not be willing to display on the mobile screen. So this from a technical point of view. It also changes how we think about API development from an organizational point of view. So now there's a question, okay, prior to that we had a backend which was maintained by the backend team. Now, who maintains the BFFs? Are they maintained by the backend team itself? Not really. So the general idea is that the BFFs should be maintained by the teams which are maintaining the client. Why is this important? It gives them the ability to kind of develop and move further without being directly dependent on the API team. So if the API implements a new feature, one of the clients can, for instance, the web team, if they're moving faster, they can quickly pick it up and start using. The mobile team might catch up. This also gives them the ability to do whatever they want with the BFF because it's tailored particular to them and belongs to them. So they don't need to kind of cross-reference their changes with the mobile team. It also gives them the ability to kind of choose their own tech stack. So for instance, if we are doing a web application in JavaScript, it might make sense to do the backend in Node.js because it's quite easy to transition front-end developers to backend developers in Node. For a mobile app, it might be different. So if they are doing a native mobile app, they can use Java. If they're doing a web-based app, like with React Native, they can also use Node. That makes sense. So this kind of gives you the ability to choose your tech stack more freely. It also relieves the effort from the API team because now they can focus on actually implementing business features. They can go back to their clear, bounded context, domain-driven design thing and not to think too much about the needs of these particular clients. Another interesting question is, okay, so we need a BFS. How many? Do we need really a single BFF for each client? Now, if we have a mobile app, an Android app, and an iPhone app, and does it mean that we need 3 BFFs? Can we get along with 2? Can we get along with 1? The question is, it depends, and there are kind of 2 ways you can look at it. One of the way would be to look at it from the user experience point of view. What does user experience mean in this context? I'm deliberately not using the word client now because even though that your Android app and your iPhone app might be 2 technically different applications, the user experience, the functionality they expose are likely to be the same. They might even look the same. They need the same API calls, will read the same data. So this kind of, from this context, it might make sense to create 2 BFFs, one for the desktop client and another to be shared by the mobile team. Makes sense from that point of view. On the other hand, if these mobile clients are maintained by different teams, we're talking about a team which does native Android development and a team which does native iPhone development, we are again introducing these dependencies. So, and now if we look at it from the organizational point of view, you might want to consider having 3 BFFs instead, so that each team would maintain their own BFF. If anybody heard of a concept of Conway's law, essentially says that your architecture will eventually match your organizational structure. So it means that if you have 2 different teams, then they'll probably eventually own different components. And trying to share this component between the 2 teams, that will just add cross-project dependencies and might be the cause why you're slowing down your development. So whatever option you choose, there's no single correct answer. We're personally leaning to the second approach, but you kind of need to just consider the 2 options and figure out where you would like your pain to be. So, of course, as usual, the BFF problem is not a silver bullet. It has its own penalties and problems. One of them being code duplication. Since often we're integrating with the same, you will expect that the integration code will be most likely duplicate across the BFFs. And there are a number of ways you can address that. In general, when you're talking about separate microservices here, a certain degree of code duplication is acceptable. So this gives you the ability to control your own code, to change it without having to look out for other consumers of that code. So with the case of the integration code, it's probably okay to have a duplicate across the BFFs. If we're talking about more complex cases, I don't know, like complex authorization of flows, permission management, logging, you might want to either introduce a shared library or even move it to a separate service, a separate downstream service, if that makes sense. Like I said, so BFF is a purely data aggregation layer. It shouldn't contain any business logic. Why is that? Because business logic will eventually, if you put business logic in your BFF, it will eventually be duplicated across BFFs, and that's a bad idea. So the business logic should be placed in the downstream services. It is tempting to put some cross-cutting concerns in the BFF, for instance, like I mentioned, logging or authentication authorization. I'm a bit torn about this because due to some technical reasons, it's really a convenient place to implement it there. On the other hand, again, is some stuff you might want to push to the downstream services. Again, is when you do this decision, you kind of just need to analyze the stuff and understand the benefits and problems of each approach. The second and the third point is, okay, yeah, we have a BFF, we have it tailored for a particular client, but now if a client needs a new field to be exposed, yeah, you still have to go and change the BFF, implement the field there, expose it, and then you go back to your UI, and then you start consuming that field. This is important because you really need to kind of control and make sure that you expose only the information which is relevant to the backend. And this introduces some manual back and forth work. And how could you address it? It would be really awesome if we could just tell from the client side to the API, okay, I want these 3 fields, just return them there. I don't care about anything else. And this is where GraphQL kicks in. So what is GraphQL? So GraphQL is a query language for APIs and also a runtime which implements this query language. It provides you a description of the data in API and gives the client the power to control what does it want to be returned by the API. And the first benefit that we are all interested in is the ability to only receive the data that we need. So with GraphQL, you can list the fields that you want to be returned. The API will return only these fields, and everything else, even if it was fetched from the downstream services, it will be just discarded. So that means you can, first of all, help the users save traffic because they're not loading unnecessary data. Plus, you give the developers flexibility to choose what will be outputted by API without actually having to make any changes to the API. So how does that look from the client side? So you have a JSON-like request on the left, which will return the make of all the cars that we have in our store, which is just sent either via HTTP query request or in a post body. And in response, you will return a JSON listing all the information that we requested. So there's an envelope with a data field, there's an old cars field which kind of matches the query that we did, and you can see we offer 3 cars and we return their makes. So now if I want more data, I can just add another field. I add the model field, and there you go, you have your model field present in the response. So this is very convenient because I can do that all from the client side. I don't have to touch the backend so long that it actually has a notion of this field and has the information to retrieve it. These queries can be a bit more complex, so you can add parameters to certain fields. For instance, I can have the ability to filter by a make. Yeah, I can also have nested queries. For instance, I can retrieve, I don't know, information about previous owners of the cars, which might also have different fields, but I will be able to pick out just the name or I don't know, the place of registration, something like that. So you have full control of what you want to retrieve. How does that work from a technical point of view? I won't get into much detail, but the idea is quite simple. So on your client app on JavaScript, you have a GraphQL client, which kind of allows you to create a query like we see before and send it to a GraphQL endpoint. The request is then picked up by the GraphQL server. And the GraphQL server, it does several important things. So it has a notion of schema. So it has a strict definition of what information it can expose to the user. So it lists all of the fields which are which are supported, which are available for querying for the user. It also lists the types and the concrete descriptions of these fields. And this allows GraphQL to do another awesome thing. It also validates your queries in runtime. So you can actually make sure that you pass the correct types of parameters, that you request field that actually exist. And if you make a typo, if you pass an incorrect parameter type, it will just trigger an error. So you have this very fast feedback of how correctly is your request structured. Yeah, so once it receives a request, it routes the request to the so-called resolvers. Essentially, each field you have in your schema can be assigned a resolver. And a resolver is just a function which basically does anything. So it might be a function that goes to a downstream service to retrieve the data. It might be a function that goes into a database and retrieves the data. It just might have some computational logic in itself. And you can either have resolvers per top-level field, like an all-car resolver, but you might also have a separate resolver for a nested field, which will, for instance, return the owners of the car from a completely different service. So this gives you the ability to keep your API very flexible and on the same time make it completely transparent to the client. So the client doesn't really care where the information comes from. He just knows the definition of the API, what it can do, and what can it request. Yeah, and in our case, so we could have 3 resolvers, so product resolver, order resolver, and payment resolver, which each of them communicating to their own downstream service. So the schema, this is really one of the major features of GraphQL. When consuming other backends, you're expected to be on your own to make sure that you craft the request correctly, that you don't do a typo, that you don't do a pass an incorrect parameter type. For instance, imagine REST. Yeah, you can pray that the API implements proper parameter validation, but in most cases, if you just do a typo in a parameter name, in worst case scenario, it might just not say anything. And for some time, you might even not notice they have a bug in your code. And the feedback loop to figure out that something is incorrect, something is not working, might be quite long. Okay. Here you get an instant runtime error saying that, sorry guy, your query is incorrect. And the schema can also be used to build very interesting tools on top of GraphQL. I will give some examples a bit later, and Oleg will actually show a bunch of them. They're really amazing. Yeah, and the schema more or less looks like this. So you define your application type, in our case a car, and you can list that it has a make, a model, a year, and an ID. So the 2 fields are strings, the other is an integer and an ID, and the exclamation mark means that the fields, they cannot be nullable, so they will always contain some value. So this definition language is really powerful and very useful. You can also use GraphQL to extract data from different sources with a single request. For instance, remember we have 2 different downstream services for cars, for products and orders. And if we were to communicate to them directly via REST, we would need to make 2 requests, which is costly and ineffective. With GraphQL, you can do that with a single request. You can say, okay, give me the cars and all orders. And again, you are free to combine how many fields you request in a single request. You can add your own heuristics to how you combine that. For instance, you can try to retrieve all of the data with a single request that is needed for a page, but you know that this one particular field is slower than the others and you don't want them to slow down the rest of the rendering. You can just load it separately. So you can decide how you do that on your own. Yes, it also supports write requests. So in a familiar fashion how you can expose a field, you can also expose a so-called mutation, which is essentially just a function which we can call with some predefined number of parameters, which can also return a value. So in this case, we can create an order for a particular car and retrieve the newly generated order ID. So GraphQL can not only be used for read requests, it can also be used for write requests. And it has a very rich ecosystem of tools. So you have the Apollo stack, which implements a client for all of the major frameworks and a client for Node.js. You have GraphQL Playground and Graphical, which allows you to kind of browse your API, interact with it, kind of an analog of Swagger for API, for REST. And you have the GraphQL Voyager, which allows you to browse the relations between the objects and the fields that you have. So all of these tools, yeah, they are very rich and very powerful. So, to wrap it up, to try to summarize what we just said, it's quite a broad topic, but I'd like to give you kind of 3 takes away. First of all, when doing a client-facing API, always consider the needs of the client when actually implementing and designing the API. That should be the driver. Embrace the fact that different clients will need different APIs, and you will end up having a certain point of duplication. That's okay. And the third takeaway is evaluate GraphQL as your protocol, as your communication language, to actually put your client in charge of how they use the API. If you would like to, if you're looking for some nice bedtime reading, there are a bunch of resources devoted to GraphQL, which you can have a look at. So there's GraphQL, their official homepage, and how to GraphQL, a very nice introduction. And there's also a web page for Apollo GraphQL, which is one of the most popular stacks for implementing the thing. And a couple of resources on the backend for frontend pattern. So an original article written by Sam Newman, the guy who also wrote the book Building Microservices, and a very nice entry on the Microsoft's cloud design patterns, which describes why you want to use it and the common pitfalls. So, thank you for that. Thank you. I hope I stood up for the expectations. Thanks.